Alright, today we're going to discuss section 4.3, which starts our talk about the zeros or the roots of a polynomial function. So here we have a polynomial function, x to the fourth plus 5x to the third minus 8x squared plus 2x minus 6. It's a fourth degree polynomial function, and we've discussed some of the things about this. The constant term is where it crosses the y-axis. This fourth exponent tells you about the ends of the polynomial function. Because this number here is positive 1, both ends of this function go up. This is also the degree of the function, and as you recall, the degree of our function represents the total number of roots that that function has. The roots are also called the zeros. And when we're talking about these, we're not only talking about the positive ones and the negative ones, but the complex ones as well. So of these four, there could be some that are positive roots, some that are negative roots, or negative zeros and positive zeros, and there could also be complex zeros. Now the thing about the complex zeros, if all of the coefficients of the polynomial function are real numbers, then our complex roots must occur in pairs. And by pairs, we're talking things like 2i and a negative 2i, or if you have 3 plus 4i as one root, 3 minus 4i is another one. These are called conjugates of each other. And so that we know that there are four roots in this particular polynomial function, there are some other things that you need to understand about those roots. And the first thing we're going to talk about are roots of multiplicity and the rule of signs. So first, the multiplicity and the roots and factors. If 3 is a root of a 0, or of a polynomial function, I mean, if it's a root or a 0 of a polynomial function, then we know that x minus 3 is a factor of that particular polynomial function. There are also going to be some examples where, or problems where it's going to say 3 is a root or a 0 of a polynomial function of multiplicity 4. In that case, then x minus 3 is still a factor, but it could be written as x minus 3 to the fourth, or you can write it out as x minus 3 times x minus 3 times x minus 3 times x minus 3. Now, anytime you have a root that has a multiplicity, whether it be a multiplicity of 1, like this one, or a multiplicity of 2, 3, 4, 5, 6, 7, 8, or whatever, then you have to understand some things about it. And when it has an even multiplicity, the graph of the function will touch the x-axis at that root. So that means when you graph this at a positive 3, the graph will just touch, and so it will either be coming like this and going back up, or possibly be coming from this end and going back down. One or the other, depending on what other things there are in the polynomial function. That's anytime there's an even multiplicity of a root, the graph touches the x-axis. Now, if we have a negative 2 is a root of multiplicity 3, then we know that x plus 2 is a factor to the third power, or we can write x plus 2 times x plus 2 times x plus 2. Either way. So then if it is an odd number for a multiplicity, or even like this first one where the 3 is a root, and since it doesn't say a multiplicity, that means the multiplicity is 1. Anytime there's an odd multiplicity, then the graph of the function will pass through that coordinate. And so at a -2, we know that our graph will either pass through going like this, or it will pass through going like that. So evens it touches, odds it runs through it. So here we have a polynomial function. It is x squared times x minus 1 to the 4th times x plus 2 cubed. So from this we know that the root in this case is 0, and it has a multiplicity of 2. Here our root is 1 with a multiplicity of 4. And here our root is a -2 with a multiplicity of 3. So then at 0, we know the graph is just going to touch either this way or this way. At a positive 1, we know the graph is going to touch either this way or this way. And at a -2, our graph is going to run through. And since this has a total of 3, 7, 9 roots in all, the leading coefficient of this, if you take x squared times x to the 4th times x to the 3rd, is going to be a positive. So that means our left end is up, or no, our left end is down, and our right end is up. And so it's going to be here. Now it could have some waves in here also, but it's going to go through this, and then at a -2, the multiplicity is 3, so it has to pass through this one. And then at 0, it's a multiplicity of 2, so it's going to touch. And then it's going to touch again at 4, and then curve back up. It cannot do anything other than that at this point, because if it curves and goes back down and then back up, that would be a couple more roots, which here we only have these 3. This maybe doesn't have to be here, and maybe it just comes straight down from there. So that's the multiplicity. Now the next part of finding roots of polynomial functions would be when you're using synthetic division. There are a couple of rules that will help you in finding polynomial roots or zeros. And those rules are dealing with the upper and the lower bound. There's a couple of them. There's a few other ones we'll deal with also today. And what the upper and lower bound rules are. The upper bound first is when you try a positive number out here. If your answer, quotient, and remainder, if they are all positive or 0, then this number, whatever it is that you tried, is an upper bound. And now, what does an upper bound mean? It means no value above it can be a root. So for example, let's say you do this and you try and a number 2 out here, and you get a 4, a 0, a 6, a 2, and a 0. Well, first off, since this number is 0, you know this is a root. And now because these are all positive and 0, 2 is the largest positive number that could be a root. And if there were a bunch of other numbers that it asked you to try, like say 4, 5, or 6, or 10, you wouldn't have to try any of these because you know 2 is the biggest one that there can be. Even if this number here is not a root, let's say we have 10 as our remainder at this point, we still know, because these are all positive numbers, that 2 is an upper bound and nothing above it can work as a root. So 4, 5, and 6 were asked to be tried. You still wouldn't need to try them because we know that here this is all positive and 0. That's the upper bound rule. The lower bound rule is similar. In that when you use synthetic division, but now when you have a lower bound, this value out here has to be a negative number. And if these numbers down here alternate, between positive and negative, if that is the case, then that number is a lower bound. And what that means is no value below it can be a root. So for example, if you do your synthetic division and you first try a -3 outside, if this alternates, so let's say we have 4, then a -2, and then 5, and maybe a 0, and then 7. This would be a lower bound because it alternates. One thing I did not mention here is when this alternating part, 0 is either positive, is either one. It can be either positive or negative. So positive, negative, positive. This time the 0 is negative, and then positive. So it alternates. Or we could have maybe this starting being negative, and then this be positive, and then this be negative. Now this 0 could be positive, and then that would be negative. Then it alternates. 0 can take on either one. And so if that's the case, then -3 would be a lower bound. And if you were asked to try like a -6 and a -10 and a -18, you would not have to try any of those because they're all below a -3. Now if they asked you to try a -2, you had to have to try that one as well because that's above -3. So that could be a root yet. And these two rules only work, lower bound only works when this value is a negative. Upper bound only works when this value is a positive. If you have a positive number out here and this alternates, it is not a lower bound because a lower bound can only be a negative value and an upper bound can only be a positive. Now the other rules that are going to help you with finding roots would be the rule of signs, invented by this man. And I'll leave you to the pronunciation. In any polynomial function, The number of sign changes that the function has is the maximum number of positive roots, differing by 2. So what that means is, looking at this polynomial function, sign is positive, here it's positive, so there is no sign change. And now we go to this term, and it's negative, so now there's one sign change. And now it stays negative, so it's still only one sign change. But here it changes from a negative to a positive, so there's a second sign change. Because of that, because there are 2 sign changes throughout this polynomial function, we know then that there have to be 2 positive roots, or there could be no positive roots. Because whatever you find is for the maximum number of sign changes, it differs by 2, so 2 or 0. So let's say we had something that had, say, 7 sign changes through the polynomial function. Then that means there could be 7, 5, 3, or 1 positive root. If you had something with 6 sign changes, then it would be 6, 4, 2, or 0 positive roots. The other part of this rule would be finding negative roots. So the number of sign changes of f of negative x is the maximum number of negative roots. So that means you first have to figure out what is f of a negative x. And if you substitute a negative into each one of these spots, you would get 4 times a negative x to the 4th, plus 5 times a negative x to the 3rd, minus 6 times a negative x squared, minus 2 times a negative x, plus 7. And then simplifying this down, negative to the 4th power is still positive, so this is still 4x to the 4th. A negative to the 3rd power is a negative times a positive is a negative 5x to the 3rd. And this is a negative x squared, so it's an x squared times a negative 6 is a negative 6x squared. Negative 2 times a negative x is plus 2x, and then plus 7. So we now can see that we have 1 sign change, 2 sign changes. So we would have 2 or 0 negative roots. And so, same thing with this. If you had something that had 7 sign changes, then that would be 7, 5, 3, or 1 negative roots. Because they have to still differ by 2. Alright, so what does that mean for our polynomial function? Well, from before, we know that there are 2 or 0 positive roots. And we know that there are 2 or 0 negative roots. And because the polynomial function has a degree of 4, we know then that there are 4 roots in all. So we have some options that could happen with this polynomial function. We could have 2 positive roots, 2 negative roots, which takes up all 4 of them. You could also have 2 positive roots, no negative roots, which then leaves 2 complex roots. You could also have no positive roots, 2 negative roots, and then that leaves 2 complex as well. Or finally, you could have no positives, no negative, which means there are 4 complex roots. In this scenario, that means if you graph it, it never crosses the x-axis. Could be something like that. And so those things will help you in finding the roots as well. And in this section, that's basically everything that you're going to need to understand. It doesn't really ask you too many times to find all of the roots. It's just going to be asking you to find the number of roots that are positive and negative, the number of roots in the entire function, if something is an upper bound or a lower bound, and things like that. So that concludes this lesson.